You know, Mr. Sams?
Yeah, I hear a bell ringing. Is
Yeah.
that just in my ears, or is that...
I think it's because you're just deranged. You got some problems in your
I don't know. The voices are telling me there's a bell going off, so I'm just taking
You know, I'm hungry.
Oh, yeah? You're hungry?
Yeah, I've been thinking about getting some chips and some guacamole.
More
jokes. Yeah, what do you think?
Horrible.
Yeah.
You know what? Do you know why I moved up here to the mountains?
I don't know why you moved to the mountains.
I did it because I don't have to worry about my lawn.
Why not? Oh, yeah, I don't have to worry about my lawn either.
Now I don't have to maintain my lawn mole or...
Oh, that's good. That's actually not so good, actually.
Dumb. I know.
You know, today we're going to be doing a lot of mathematics in our assignments.
Yes, we are.
And so we're going to be working with some multiplication. Multiplication.
We have students in here giving us just the
Is that a good joke or what?
Eyes
Hey,
right
today
now.
we want to talk about titrations, and actually, before we get into too much titrational discussions, oh, did you guys see this? This is so cool.
Yay.
Yeah, Sams versus Bergman. There's, of course, the tall guy with, he never shaves.
Never shaves.
And
Once
then
a week,
the
whether I
smart
need it or
guy
not.
right here who's about to set him on fire. But, of course, he's going to add cesium to water, and I'm going to add thermite. I think a thermite beats...
I don't know. I think we're both going to blow each other up.
It's not going to be a pretty scene, is it? Not at all.
Hey, do you know where a king keeps his armies?
I don't know where King keeps his armies.
In his sleeveys.
In his sleeveys.
His armies.
Army, arm in the sleeve. I get it. Okay,
Yeah,
okay. I am very slow.
Don't you love bad
pun
jokes?
Okay, so
we should probably get started here.
We probably should, because we're just taking a minute of your time.
We did.
Okay. Adding strong acids and bases to solutions. All right. Now, when we add them together, this is called actually a titration.
A titration, yeah. You did some of these in regular chem, and in your big gigantic project, you did some titration as well.
You've got the fancy burette, and you have the burette, and you add chemicals to the burette.
Yep.
And that's how we kind of do that. But we want to know when you've reached the equivalence point.
Yes.
And what happens at the equivalence point?
Well, that's when the moles of the acid.
The moles of acid.
No bad joke there either, just moles.
Just moles.
And equals the moles of base.
That's right. So we're looking for the equivalence point. Equivalence, equal point, right? The equal point, so that's the equivalence point, and that's when something's equal.
Right.
And in our case, what we care about is when the moles of the acid are equal to the moles of the base.
Right.
Okay? Now, there are two ways that you can tell if you've reached the equivalence point.
Yeah, the first way you've already done, and that's using an acid-base indicator. Usually you're going to see a color change of some sort.
So the indicator, there would be a color change.
Mm-hmm. The most common one we use is phenolphthalein.
So there's two you should know. There's phenolphthalein. Phenolphthalein is
P-H-E-N-O-L.
Phenol,
P-H-T-H-A-L-E-I-N.
A-L-E-I. Phenolphthalein is, it's pink in a base, and it's clear in an acid. These are just good things to know. And then, of course, a bromothymol blue.
BTB.
It is a blue in a base. And it is a yellow in an acid. Okay? Now, so you're looking for some variety of color change.
Yep.
The other way is to actually chart the pH with something called a pH meter. You've had experience with that.
Yep.
If you haven't out in the internet land, it's just a device that measures pH.
Yeah.
And you measure the volume a little bit at a time, and you record the pH, and you're looking for the what?
You're looking for the steep part of the curve where it makes a big gigantic jump in pH, going from very low to very high, or very high to very low, depending on which direction you're titrating.
And so it's the center of the steepest
part
of the
graph. Middle of the
So
steep
what
part.
you're actually looking for down here, this one looks like it's about 35 milliliters on this particular graph that's in your notes. And this one has a pH of 7 at the equivalence point. It isn't always a pH of 7, and we will learn about that quite shortly. All right, folks, you need to get out your calculators because we will be doing lots of problems. Problem. Now, you're going to watch us, and we're going to do the problems, but I really think it's good that you solve the problems with your own calculator at the same time.
Yep.
And check that Mr. Sams is doing his work right.
That's right. I do make mistakes periodically.
Occasionally makes mistakes.
Yeah, I get a little distracted.
Okay, so now what we're going to do is we're just going to do a boatload of problems. All right,
Yeah.
what is the pH when 20 milliliters of 0.25 molars hydrochloric acid react with 0.35 molars of sodium nitrite?
Okay.
Now, first of all, what I want to realize is I've got HCl. Now, actually, let's back up for a second. This is very important to note is that whenever you do, it's all about the reactions. If you get the reactions down, the math is easy. All right, here's my rule. Acid, write this down somewhere on your notes. Acid plus base, always. Rule number 1. Acids react with bases. Acids do not react with
more acids.
More acids. The second rule is partners.
P-A-R-T-N.
I got an extra E in there.
So our science teachers.
Partners always where?
On opposite sides of the arrow.
Opposite sides of the arrow.
In the reaction,
In the
product
chemical reaction. So one partner here, one partner here. What do I mean by a partner, Mr. Sands?
Like a weak acid and its conjugate. Things that are only different by a hydrogen ion.
Okay, so now let's think of this. We have HCl.
Mm-hmm.
All right,
pretty.
HCl, I can't write today. And we have sodium nitrite.
Mm-hmm.
So NaNO2. Now, we need to look at these. We are not going to just do that. That's wrong. So what I need to do is I need to go, okay, now what am I going to do?
Right, we're looking for things, what makes something acidic and what makes something basic. So
this is a what, Mr.
That's
Sands?
a strong acid. So all we really care about there is an H+.
So all you care about is the H positive from this guy right here. Yep. Okay, and then from the NaNO2.
Yep, that is NO2 is the conjugate of a weak acid. So it's the conjugate base of a weak acid.
So who do we not care about?
We don't care about sodium there.
So we care about the nitrite. Now, what's the form of the nitrite?
That's NO2 with a -1 charge.
You must have the -1 charge. Now, this is an acid, and this is a base.
Yep.
We can mix the acid with the base.
We can.
So our reaction is simply H positive plus NO2 negative makes HNO2.
Yep.
Now what we can do is we can do an ice table. Or it's actually more of a BC.
Yeah, this one you got to do
a table.
Yeah, you got to do your stoichiometry first, and then you do your equilibrium. Let me say that again. You do your stoichiometry first, and then you do your equilibrium. So you do the stoichiometry first,
second,
and then you do the equilibrium.
You don't do the equilibrium
first? No, I'm pretty sure you do the stoichiometry first.
Always?
Always.
Okay.
And then you do the equilibrium.
What do you mean by the stoic first?
Well, we're adding acids and bases, and they're going to react with each other first. And then, if you notice our product there is a weak acid. Weak acids have to do some equilibrium stuff whenever you throw them in water. So first you react your reactants to make your product, and then that product does this little equilibrium thing.
Okay,
and
so
you'll
see what we mean by this. Now, first of all, we can now work with millimoles. So if we go back to our problem, we have a particular variety, 20 milliliters of 0.25 molar. So, of course, you got to remember, this is very important. M times V is moles.
Yep, and that gives us...
You can take them and multiply them. You get them both. So 20 times 0.25, so that's the H positive, is what, Mr. Sam?
That is 5 millimoles.
5 millimoles. And if we do the nitrite, we go back.
20 times 0.35, which is 7 millimoles.
So we've got 5 and we've got 7. Now, I can quickly do this. It's not terribly hard. I'm going to run out of, looks like H, minus 5. There'll be none of this.
Right. Since we're titrating to an endpoint, we're always going to use one of these up.
Now, how much nitric acid did I have at the beginning?
None.
I had none, because we did not have any nitric acid.
Nope.
And this will be then plus 5, and that's 5.
Okay.
Now,
so now we've done the stoichiometry. Now those are millimoles.
Amounts. We have 5 and 2 of, wait, Mr. Sams, NO2 negative and HNO2 are...
Those are partners.
Partners! Oh, yes, that's right.
Hey, guess what? Those are acid-base partners.
So we can, and guess what? We have a significant quantity...
Yes, we do.
...of each. So that means we can use the...
David Hasselhoff equation.
David Hasselhoff.
Henderson-Hasselhoff equation.
Hasselhoff equation.
Hasselbach.
Hasselbach. Whatever his name is. Okay, well, what is that equation? It's been a couple of days since we probably saw that, folks. It's pH equals pKa plus log of the base over the acid. Now, we do need to find the pKa.
And I need to grab a textbook and
look
that up.
First of all, we need to know the Ka. The Ka of HNO2 from the book, or the table in the back of your book.
It's coming. Page A24.
You are in the right page,
Look at that.
Mr.
Hey,
Sams.
I finally figured out where it was. HNO2,
there at the top.
4.0 times 10 to the negative 4.
4.0 times 10 to the minus 4. So if I were to take the pKa, that would be the negative log of 4.0 times 10 to the minus 4, and that would be 3 point something.
3.40.
3.40. So I can just say the pH will be equal to 3.40 plus the log of the base over the acid. Now remember, a very cool thing we learned last time is that if we have millimoles and you have a buffer problem, it is the same. You can use the millimoles. Now the acid, of course, is HNO2, and the base is the NO2 negative. The acid will always have the extra H, ladies and gentlemen. So this will be the base over the acid, so it's 2 over 5, right? So log of 2 over 5, we just then say, and that equals...
Plug it in, you get 3.00.
3.00. Wow. A perfect pH. Okay, nice. Okay, that was the first example. We'll try and cover these next ones a tad faster.
Yeah.
Okay, now we have a different situation.
Yes.
All right, we've got the nitric acid, and we have. Notice, first of all, I am ignoring the numbers. That there's 15 milliliters, and I'm going to worry about all those numbers later. And I've got this thing, and I've got this thing. Now, this looks a little confusing, but this is your acid because it's got H's in a couple of places, and this is the salt of that. So let's kind of, Mr. Sams, one thing I know that you like to do is let's ask ourselves what is in the beaker.
Let's get into the beaker. Put on your little scuba suit, shrink yourself down, jump in the beaker.
It's like being in Mrs. Frizzle's class. Remember, you could
get
shrink
in your
yourself in a
magic
magic
school bus. Shrink down.
So we have nitric acid. I'm going to put that on the outside here for a moment. But when we write nitric acid in the beaker, what do we really have?
H+.
We have H positive and
NO3 minus.
NO3 minus, okay. And our second chemical is this HCO2H.
Yep.
HCO2H. That is a weak acid, and so it stays together, and that's just that.
Yep.
And our third thing was the NaCO2H.
CO2H.
And so this is a sodium compound, so the sodium, of course, dissociates. So we have sodium ions, and we have NO2H, negative, right, because it dissociates.
CO2H.
All right, sorry, CO2H, my bad.
Yep.
Okay, so now let's decide who reacts with who?
The acid reacts with
the base. So we've got to find an acid, okay? Now let's identify. This H positive is a strong acid, right?
Yep.
And this right here is a
weak acid.
A weak acid. So we can't obviously react those together.
Nope, they will not react.
And then we have the nitrate and the sodium. What are we going to do with those?
Ignore them. They're spectator ions.
They're spectators. They're not important in this whole thing. And the third thing that we care about is we have a weak base.
Conjugate base of a weak acid.
Conjugate base of this weak acid.
Yep.
So this is a weak base. So who's going to react with who?
The strong acid is going to react with the weak base.
Now, why wouldn't the weak acid react with
They're partners. Partners do not react with each other. They show up on opposite sides.
So these will react together.
Yeah.
So the reaction, folks, is going to be H positive plus CO2H negative makes HCO2H. I got it. Now we can do our BCA.
Because we do the stoichiometry first.
That's our. Now we've done the reaction first. Now we're going to do the stoichiometry first. Now we have to go figure out how much of each have we got. Now we've got quite a bit of chemicals here, all over the place here. I've got 15 milliliters of 0.2 molar. So 15 times 0.20 would be the nitric acid or the H positive, and that's going to be how many?
3 millimoles.
I got 3 of those. And then I go back to this one and I say, all right, how much of the buffer? 50 milliliters.
Yep.
Of 0.25, so 50 times 0.25, was that the acid or that the...
that was the acid.
Of the acid.
Yep.
Is what?
Is 12.5.
12.5. And then the sodium CO2H...
is 50 times 0.3, which is 15.
So 15. So guess what? We have numbers. Who's going to run out of first? Looks like the hydrogen.
Yeah, we're going to run out of the hydrogen.
Hydrogen right there. Yep. So that'll be minus 0.3, or minus, not 0.3, pardon me. Minus 3.0. There's nothing there. This will be minus 3, and this will be plus 3. So that, of course, is 0. Looks like a 12 to me, and that looks like a 15.5. Guess what, Mr. Sams? We have a buffer.
We do have a buffer.
And because we have significant quantities, we can 12 of one and 15.5 of the other.
Yes.
So we can use Mr. Henderson-Hasselbalch equation.
Yes, we can.
So we can say pH equals the pKa plus the log of the base over the acid. Now this is a different chemical, so the Ka of this acid of HCO2H
that is formic
from
acid.
The table is formic acid.
It's 1.8 times 10 to the negative 4.
1.8 times 10 to the minus 4th. We take the negative log of that. The pKa is equal to, Mr. Sams is furiously typing this in his calculator.
Yeah, the pKa is 3.74.
3.74.
And then plus the log.
Oh, I see. Okay, all right. So you would say equals 3.74 plus the log of the base over the acid. Now, which one is the base? Let's go back for just a moment and take a look. The base is this guy, the CO2H, and then this is the acid. So it'll be 12 over 15.5. So that's 12 over 15.5, and then you do the math.
You get 3.63.
3.63. Nice. Okay, let's move on to problem 6.
Yeah.
Now we have a strong base and a buffer. All right, it's just the same thing. We just got to
exactly the same thing. Look, it's even the same buffer solution.
Oh, that was nice of me, wasn't it?
It was. Okay.
All right, what have I got here? All right, I've got some sodium hydroxide. So I'm going to draw my beaker. Let's all draw a beaker. All right, sodium and hydroxide. I break it apart because it's a natural motion. What?
Your beaker.
That does not look like a drum.
Yes.
That is a beaker.
I'll shut up.
Okay. Okay, and we still have the HCO2H, and then we have the sodium
Christmas, can you tell?
and the CO2H negative. So now let's identify who we can ignore. I think it's pretty obvious. Nah.
Sodium goes away.
So now we've got the hydroxide, which is a strong base.
Yep.
I have the acid, which is a weak acid, and I have his partner, which has to be a weak base.
Yep.
So whom is going to react with whom?
Strong base.
Strong base with weak acid. So these guys are going to react together. So let's write this out. So you'll say hydroxide plus HCO2H arrow. Now the partner, I think it's probably easier to say the hydrogen is going to get the hydroxide and just makes water, HOH, plus CO2H negative.
Yes.
Now we do our BCA, and our quantities
we have 15
the M of E mole thing.
Yep, 15 milliliters times 0.2. So we have 3 millimoles of the hydroxides.
3. I think they're the same amounts.
They are, yeah. So
12 or something.
12 and a half of
which
the
one?
acid.
12.5 of this guy.
Yep, and then what
15
was it?
Wasn't it?
1.5, yeah.
1.5?
Or 15. You're right. Sorry.
So 15?
Oh, yeah. 15. You're
okay.
Right. I'm sorry, I missed a decimal in my calculator.
Minus 3, 0, minus 3, that'd be 8. 9.5. And then plus 3, we're at 18.
Yep.
Guess what we have?
We have
a buffer. And we can use the same equation because, of course, it's the same buffer of formic acid and its partner. So we're going to use this 3.74.
Yep.
So the pH will be equal to 3.74 plus the log of the base. Now, again, the base is the 18 number, and then the acid is the 9.5. So I say 18 over 9.5, and that just comes out to
4.02.
4.02. That's it. Not hard. There is an alternative way to solve these, by the way, guys. Let me just quickly show you. We're not going to do it. But, of course, what you could then do is you could take your HCO2H, dissociate into H positive, plus CO2.
Alternate meaning?
Plus HCO2. The other.
You didn't want to use Henderson-Hasselbalch?
If you didn't want to use Henderson-Hasselbalch, what you would do, this is a pain in the butt, frankly.
It is.
Is the HCO2H was 9.5, but you actually have to work in molarities. So you take 9.5 divided by the total volume.
Total volume.
And then you would take, we're not going to actually solve it.
No.
And take 18 over total volume, and this will be 0. You would say minus X, your value from the molarity, minus X, and this will be plus X, and this will be this number, this will be plus X. It'll be another number, call it a square, plus X, and then you would say the Ka equals, and you would say X times, I'll call it square plus X in parentheses, over circle minus X. You solve for X, find the hydrogen concentration, take the negative log of that, and you get your answer. And guess what you'd get? 4.02.
4.02. For something
you get the same
pretty
answer.
darn close.
So if you have a buffer, you do not want to deal with that route.
No, just use Henderson-Hasselbalch.
In the butt. Okay, number 7. It's Henderson-Hasselbalch. Get it right now.
Sorry.
Okay, strong base and weak base buffer solution. All right, so other examples. There's just a myriad of examples. All right, so let's go back to my beaker. My beaker. All right, what have we got? We've got sodium hydroxide, so we've got Na positive and OH negative. And we have this ethylamine. That's just a weak base. C2H5.
Yeah, it's one of those ammonia type things.
It's got that N in there, right? And then this one is a little confusing. It's ethylammonium chloride, so that'll be C2H5NH3 positive and chloride negative.
Yep.
Who gets to go bye-bye?
Sodium and chloride.
So we have now here hydroxide, which is a strong base. This, of course, is a
weak base.
And then last one is a weak acid. So you can take your strong base and react it with your weak acid. So our reaction will be hydroxide, OH negative, plus CH... what is it again?
C2H5NH3 plus. C2H5.
2H5 NH3 positive. That's right. Okay, make C2H5NH2 plus water. All right, we'll do our BCA. Now we do our
so
M
we gotta get our,
times V equals moles
we got
for each
40
bubbles.
milliliters and 0.25 molar sodium hydroxide, so it's 10 millimoles of hydroxide.
10 millimoles. All right, C2H5NH3. We'll do MV.
Yep, C2H5NH3, that's 40 millimoles of that one, and 40 millimoles of the other one. 100 milliliters times
the water.
0.4.
So we'll subtract 10.
Yep.
0 plus 10. No, pardon me. Minus 10. I was checking your...
Yeah, I know.
30 plus 10, 50. So we got 30 and 50. Guess what we've got?
Buffer.
We have a buffer. Now, this is a little bit tricky. Is it still pH equals pKa, A plus the log of the base over the acid. But if you were to go in the back of your book, you would find that the Kb of C2H5NH2 is equal to
5.6 times 10 to the negative 4.
So you have to look that up in the back of your book. So we need to find the, I would actually find the pKb, Mr. Sams, or I don't know, there's a number of ways to get this.
Yeah. Oh, I just took 1 times 10 to the negative 14.
All right. So the Ka would be 1 times 10 to the minus 14.
Which is Kw.
Divided by the Kb, which of course is this number.
Right.
Equals
1.79 times 10 to the negative 11.
And if you then take the negative log of that,
Yep.
of the Ka, that gives you the pKa, which is
10.75.
10.75. So now I'm going to use my equation, pH would be equal to 10.75 plus the log of the base over the acid. So let's go back and figure out who's the base and who's the acid again. The base, of course, is the one without the charge. So he's the 50. He's the base. That makes him the acid. So it'll be 50 over 30, right? 50 over 30.
Yep.
Those are within a fraction of, or a factor of 10 of each other. And so pH is what?
10.97.
1097. Okay? All right, we're getting there. All right. All right, now let's do a different one. We have sodium hydroxide, big beaker here. I'll just do a square. We've got sodiums. We've got hydroxide. I dissociate that, right? And then I have propanoic acid. I've got HC3H5O2. I only have 2 things, don't I, Mr. Sanders?
Looks like it.
I mean, well, there's 3, but I can ignore the
sodium.
All right, so obviously this is a base, strong base, and this is a weak acid. So I'm just going to react those together, and I'm going to say OH negative plus H, which one is this?
Propanoic acid.
HC3H5O2. C3H5O2, and that's going to make water, and his partner, remember, partners on opposite sides, C3H5O2 negative. And then we'll do our BCA. Now, how many millimoles of hydroxide? If we go back,
have 10. It's 40 milliliters times 0.25 molar.
So this is
millimoles.
10 millimoles.
And then we have 20 milliliters of 0.5 molar, which is also 10
moles. Oh, 10 millimoles. Okay, this is interesting. How much of this do we have?
None.
None. Okay, so this will be minus 10, 0, minus 10, 0, plus 10, 10.
Yay, we have a buffer. No.
Wait a second. Can we buffer?
Don't have a buffer.
Do we have partners? We have 0 of our propanoic acid, and we have 10 of our propanate.
Propanoate, yeah.
Propanoate or propanate?
I think it's propanoate.
Okay, whatever. Close enough.
All right. It's kind of fun. Banana fat.
Now, guess what? We cannot do Henderson-Hasselbalch. So now we need to take this amount, and we need to write a new reaction. And the reaction, of course, is when in doubt, you always react something with
water.
So I'm going to react with water. Now, I'm going to write HOH. You will see here, double arrow.
Because this is the equilibrium step. We've done our stoichiometry.
Now we're going to do equilibrium.
Now we do the equilibrium.
Henderson-Hasselbalch is doing equilibrium.
Right.
Shortcut.
It's just the easy way. Yeah.
So now I'm going to say HC3H5O2. See, this hydrogen connects here, makes his partner, right?
Yep.
Plus hydroxide.
Yep.
Now, we have a particular... Now, this is an ice table. It is not a BCA table.
No.
Now, when can we use millimoles, Mr. Sams?
When we're doing the BCA table and in Henderson-Hasselbalch.
Yes, you can use it in Henderson-Hasselbalch.
You cannot use them in an ice table.
You must use what?
We must use concentration.
So we must work in concentration. So if I go back here, I had 10 millimoles.
Yep.
So 10 millimoles divided by the total milliliters.
Total volume. We had 40 milliliters of the base and 20 milliliters of the acid for a total of 60 milliliters.
So 20 and 40. These were mixed together.
Yes.
This is 60 milliliters. So 10 over 60 is what?
0.1666666 repeating. There you go.
0.167 molar. That will be my beginning amount, 0.167. And guess what? We've done a problem just like that. Did you do that right?
Yeah. I'm just going to say my son's learning his numbers, and first time he saw 20, and he was learning, he called it 20-0, because it had an O at the end, so 20-0.
You've actually done a problem like this in the previous chapter, but basically you have the salt of a weak acid, but we've produced it in a reaction, actually.
Yes.
So it's a little bit different, but not really. The problem mathematics is the same. Now, this right here is not a Ka problem.
No, this
is a hydroxide. So we need to find the Ka of this is from the back of the book.
The Ka is 1.3 times 10 to the negative 5.
So if you do the math, the Kb
is 7.69 times 10 to the negative 10.
So I need to use that in my calculations. I'll say 7.69 times 10 to the minus 10th would be equal to x squared over 0.167 minus x. I solve for x. Now something I've noticed on some people's tests, x is actually the hydroxide concentration. I think it's important that you actually write brackets hydroxide.
Yeah.
So now you use your solver. Mr. Sams is furiously doing the solver
frantically
game. And he's solving for x. And x is?
1.13 times 10 to the negative 5.
So now what we can do is take, and that's molarity, or molar, you would take the negative log of that, and you would get the POH, which is the negative log of this number here.
4.95.
4.95. And of course, pH
9.05.
plus POH is 14.
Yes.
So then therefore the pH 14 minus 4.95, I'm not going to write it down, is?
9.05.
9.05. And actually, let's talk about this particular number. What is this particular thing called when you run out of everything? Yeah, here it is.
Yep.
This is the screen I want.
You
have 0 here and 0 here. This is technically called the
at the equivalence
point. And what is the pH at the equivalence point? 9. It's not 7.
Right.
Because of the presence of the propanoate ion, or propanate ion. I've always called it propanate. Oh well, that's okay. Because we have this whatever, this ion right here, this guy, and since he is a weak base, the conjugate base of the weak acid, propanoic acid, then it's basic at the equivalence point. So, and the pH is higher than 7, it's 9.
Yeah.
So it totally makes sense. I think we've got a couple more to do.
We do.
All right, we'll be done here soon.
Got 4 more. 5 more.
Have mercy.
I know. What are we thinking?
Okay. This is such a good thing. If you understand this, you are so set to do any acid-based problem. Okay, what have I got? I've got sodium hydroxide, so Na positive and OH negative.
What's BEP?
No,
I know what that means. Never mind.
And then we've got
That's a clue for us.
C3H. It is a 5O2. These are the exact same chemicals, so the exact same equation is going to apply.
We just have different quantities of them.
Different quantities. So we have hydroxide plus C3H5O2. Same exact reaction makes water plus C3H5O2 minus. Now, when I do my BCA table, what are my numbers, Mr. Sams?
We've got 42 milliliters of the base at 0.25 molar, so that's 10.5 millimoles.
I believe this one's still 10.
And then that one is still 10, yes.
And there's 0. So we'll go minus 10, 0.5, minus 10, 0, plus 10, 10. Now, this is an interesting situation. Interesting situation.
It's not a buffer.
It's not a buffer. Now you say we got 2 things, Mr. Sams.
We do. We have a base and a base.
Oh, you see, this is a strong
base,
and this is a
weak base. In which case, the strong base wins.
So
we don't care about the weak base.
In this case, there's no equilibrium. You just will take the concentration of the hydroxide will be equal to 0.5 millimoles divided by the total volume. Now, what are 2 volumes in this problem?
Total volume. We had 42 and 20, so divided by 62.
42 and 20, so this is 60 milliliters. So when you get this, the molarity is
0.00806.
0.00806 molar. That's the concentration of hydroxide. If you take the negative log of that, you get the POH, and that would be what?
2.09.
2.09. Subtract that from 14.
11.90.
11.91. Okay, so that's the answer. You ignore this.
Yep.
This is unimportant. No importante. Not at all. You just do the 11.9, or just the excess strong base. So if you have excess strong base, you just say 11 point, do the math here to get this number, take negative log, and you're basically basically
Basically.
are.
Oh, that
done.
goes with our lovely pun.
Ooh, basically done. Yes, okay. But you get it base. Now, one thing I want to warn you guys is that we are really hammering through these problems very quickly.
Yep.
You probably need to pause this video occasionally and say, what did he do? Back us up, and then make sure you follow along. It's critical that we understand this.
Yeah.
All right, this podcast is getting long, so what Mr. Sams and I are going to do is we're going to pause, or we're just going to have a 15.2A and a 15.2B. And so you'll need to watch them both. I must confess, I'm sorry. So you need to find the 15.2B, but we're running out of time and our class is about to walk in, and so we want to make sure that we can't do it while class is going on. So we'll see you back on B in just a moment. Bye.
All right.